Okay, my class. Okay, today's class won't be super easy. Let's see how many are there. Okay, I have to try to move along. Otherwise, I do tend to run out of time when I teach online. That happened this summer. I taught this class this summer, and it definitely at the end of class I definitely run out of time. If I run out of time, of course, I have to start cutting things down. I'm already going to cut things down as it is. Of course, if I don't get to it, then I can't get to it. But I have to try to avoid a little bit. At least I don't like to cut everything from the end. That just doesn't seem right. So at least get to RLC circuits, which is something that engineers, most of you guys are engineer majors. So, you know, circuits, it seems like I should definitely cover circuits. We did do RC circuits. Very briefly, we talked about there's a differential equation, and then you solve it, and then you can see how you're charging a capacitor. We can give practice exams. I don't want to give the practice exams just yet, the practice problems just yet on that, because that would take, I know when you're doing practice problems, all of a sudden you spend a lot of time on that. I don't want to, I have to move ahead, but I will back up. Provided I've made progress on the PowerPoint, so you know, so I can get to the material, then I will definitely find the time a little later to back up and do a few practice problems. So today I am going to press ahead a little bit. Okay, so I'll finish up what we're doing, sure, but I want to press ahead to the next PowerPoint as well, to kind of like see them in combination. If I wait a long time, then by that time, you know, you don't remember this part as well. So by doing it today, you remember this PowerPoint. This PowerPoint was about charges moving in external magnetic fields. But then we can put it together with next PowerPoint and do the combined picture. And then we'll get back to the problem of two protons moving together. Make sure we know how to do that. Also two wires side by side. And then next week, I'll try hard to find a time to do practice problems from some of the stuff we already covered. That may go easier since you already would look at some of that. Remastering physics, yeah, otherwise I'm going to run out of time at the end. So I'm going to have to press ahead a little bit this time and try to put together the two pictures for you. Okay, so let me remind you again why I must do this. In this PowerPoint, they had a segment there where all of a sudden they're talking about magnetic fields produced by wires. All of a sudden there was a PowerPoint up here, and I jumped through it because I said, oh, I don't want to talk about this now. It's up here somewhere. There you go. There is a wire, carries a current and produces a magnetic field. Actually, that should be really the next PowerPoint, really, but they put it in here. So I want to go fast so you can see the connection, you can treat both problems. This part, the magnetic flux, I can come back to it. I don't want to spend too much. There's not much that comes out of this magnetic flux. let me just cover this PowerPoint slide very quickly, move on. It's not that useful. Tell you why it's not useful. Then I will do the torque stuff. That's also a little tricky. I should do that. Then immediately after that, I'll go to the next PowerPoint so that we can combine the two PowerPoints in our mind. This one, and then the next one is external field. Then how do you produce the external field? That's the next one. Okay, but in any case, just very briefly, this PowerPoint slide here, we're not gonna use it that much, okay? But this tells you why it is that we don't have a Gauss's law for magnets. Remember how we did Gauss's law? Let me remind you, it's kind of like, okay, it's easy to forget what you're doing that. Remember that to use Gauss's law, what we were doing is we're calculating fluxes. So instead of talking about the electric field itself, we kept talking about the flux of the electric field. And then the Gauss's law said, oh, the flux of the electric field equals the charge inside divided by a constant epsilon naught. So maybe there could be the same thing for magnetic fields, since they're very closely related, magnetic fields and electric fields. However, I already pointed out that magnets cannot just be North Pole or South Pole, so you cannot just have a positive without the negative. So when you actually try to do Gauss's law for magnets, sure, you could do a Gauss's law for magnets, but you end up getting that the flux of the magnetic field equals 0, not equals the charge inside. Remember, it was the charge inside because you can have a positive charge. The negative charge doesn't have to be there. But with magnets, they have North and South Pole, and there was up there, you saw that if you break up the magnet, then you still have North and South Pole. So that's kind of shocking that that's true, but it is true. So therefore, this is not that this cannot be used, is that it's not that useful. Of course, you could try to use it for something if you wanted. The flux of a magnetic field must equal 0. So that's why they call it Gauss's law for magnetism, right? That's what's in here. Well, that's fine. It turns out this is not that useful. So then we're gonna have a different version of Gauss's law for magnetic fields that's more useful. Okay, so it's called Ampere's law. We'll go to that. That's in the next PowerPoint. Again, there's nothing, this is true. There's nothing wrong with this. That's true enough, but it's not useful. So we're not really gonna use this that much, so we can move on pretty quickly. This would be the equivalent statement for electric fields. Now you have this, instead of the charge inside, you have 0 there. That's what I'm trying to say, okay? So that doesn't turn out to be so useful, so let's move on. Let's not spend a lot of time on something that's not that useful, okay? That's not a good use of our time at this point. So we'll move on, not gonna use this that much, not gonna really show up in the exam, okay? So where were we from the last time? Well, we had talked about forces, but people like to talk about torques as well. It's kind of interesting. There's a relation. I'll give a few examples of that. So they're telling you here, they're giving you a formula for the torque. The truth is you don't have to use this formula for the torque. So torques tend to rotate, right? So forces, so I'm gonna do examples in a second. So this, I do wanna clarify this part. So I'll set up a problem once I'm done talking about it this way. Let's just use the formula. It goes a little quicker when you're solving problems if you use the formula. Now, you could use a different formula from Physics 50, the one about what is the torque on something, and in Physics 50, you wrote it like this. Torque equals R cross F. So we know the forces. We just covered the force last time. You could always use this formula to calculate the torque on a loop by calculating the forces on each piece and so on. But let's just go ahead and use it. It's a little quicker. It's open notes. You can use whatever formula. It doesn't really add any complication to cover the formula. And you can write it down for yourselves when you're taking the exam. And it will go faster if I ask you something about this. It will go faster to use this formula. Okay, so what is this formula then? So let's just use it since it's in here. So they're defining something called the moment, the magnetic moment here for you. And the magnetic moment is just the current. So you have a loop, and what you want to know is, will there be a torque on the loop? Now you can calculate forces. We're going to talk about forces again in a second. But what you would also like to do, in addition to forces, you would like to know, are the forces creating a torque? Are they twisting my loop, yes or no? Okay, to do that, all you have to do is you calculate mu, and mu is I times A. Okay, that's the magnitude of it, but now they're turning it into a vector. Okay, so you gotta keep that in mind. This is just the magnitude here, IA. Now, sometimes in some situations, what they have is they have multiple, they go around multiple times around the loop. So they have one wire, but it wraps around n times around the loop. So in that case, you will find the version of this formula in which they put n here. So n is just how many times around the loop does your wire go. So if it's one wire, but it goes around once, then it's IA. But if it goes around twice, then it's 2IA. Okay. So anyway, so that's the same formula though. There's nothing different. This n is the number of turns of the wire around your loop. Let's just keep it simple. So let's forget the n for now. It makes no difference really. It's just an additional. So how many loops, how many times the wire goes around? We'll just do IA right now. So one loop, just don't go around several times, just once. So then n equals 1. This is the formula. Okay, so A is the surface area of the loop. Okay, but you turn this into a vector. And this vector, you know, the way people like to talk about this, they use an additional right-hand rule. So we're going to use multiple right-hand rules. If you want to do this fast, we already did a right-hand rule. The right-hand rule we've done so far corresponds just to the cross product. Whenever you see a cross product, you use the right-hand rule we've been talking about. Now here they like to talk about an additional right-hand rule. That's why they put a right hand in there in that drawing. That's why it's in there. Let's learn it. You don't really need it. Again, you can just go back to the basics. What is a torque R cross F? And then that's it. But here they just want to go a little faster for you. So they're creating an additional right-hand rule, and then we're going to have yet another right-hand rule. So it will be 3 right-hand rules in 2 chapters, in two PowerPoints. So in this right-hand rule, what they're trying to do with this one is they're trying to make you go fast so you don't have to think about it too much. So they're saying, okay, great. This is the magnitude of this vector, this magnetic moment that will allow us to calculate torques. But I need to know the direction. So there's always this right-hand rules in the end. What you're using them for is just to solve a sign problem. Is this a this way or is it the opposite way? Okay, that's it. That's what the right-hand rule is doing. There's not doing anything else, really. It's a sign issue that you're solving with this right-hand rule thing. So here what they're saying is, what you can tell they're saying is that you get your fingers, you wrap your fingers in the direction of the current for this particular right-hand rule. And then your thumb points in the direction of the vector magnetic moment, of the magnetic moment vector. Okay? Now that's pretty amazing to create a right-hand rule just for this, but hey, it goes faster, might as well use it. Then you can use it in the exam, go a little bit faster in getting answers. Okay. So I would suggest just learning it. It's not that big a deal. So basically what I just decided, because of the right-hand rule for the example in the PowerPoint, I'm going to wrap my fingers and this drawing, generally what I will do actually when in the exam and also in my examples, because I cannot do 3D drawings like this, I will always, as I mentioned before, I will always align the loop with the page. Right? And then I will tell you is the current clockwise or counterclockwise. So, and then the only other thing is in what direction is the magnetic moment. So let's do that. Instead of doing this 3D drawing, I can't do that. And I can't keep it for you in the exam. I mean, there's nothing wrong with it, but you know, it's trying to do perspective. I can't do drawings of perspective on the fly, certainly, and in any case, not even on the fly. But in any case, so in the exam, instead of that, what we're always going to do is we're going to just choose the plane of the computer, of the screen. That's my loop, right? Then I have to decide what direction is the magnetic field in this drawing, and also what direction is the current. Is it clockwise or counterclockwise in my loop? So in this case, the way they drew it, it would be like I would be that way, right? So it would, in this case, it would be counterclockwise, right? I'm just taking the loop that they have and I'm putting it like this with the screen. So now this is the I is counterclockwise. So how I would talk about it, instead of talking about it off to the left, that doesn't really help. So I would be out of the computer screen or into the computer screen. So my right-hand rule in this situation says, I wrap my fingers around the current, and then my thumb, I'm using my right hand, this is my right hand, my thumb points out of the computer screen. So in this drawing, I would have to draw the thing, the mu, the magnetic moment is like this, is coming out of the computer screen. That's my mu. Okay, that's my magnetic moment. Okay, is that clear? So it depends on I and A, and mu is coming out of the computer screen in this situation. Now, in order to figure out, now that's the mu. Now you calculated the mu. Now what you're gonna do is, the mu has a magnitude and it has a direction. You use the direction with the right-hand rule. Okay, clear. So the mu is coming out of the computer screen. Now what you have to figure out if there is gonna be a torque on this loop. Now you have to talk about the magnetic field. Okay, now let's think about things in the drawing. Again, part of the problem here is not necessarily a formula. It's pretty simple. It's mu cross B. I mean, it's a cross product, but the problem we run into is the drawings just throw people off. So in order to help with that, I'm always going to do the same kind of drawing. So once you get used to the drawing, it's not like you have to think about it over and over again. Okay, so let's get used to drawings that are like the one I drew, not like the one in the PowerPoint. Those are the drawings that will show up in the exam. Okay, so now I have this drawing and I have to decide there is an external magnetic field. Okay, so I can pick several things for this. This is actually a 3D drawing because I'm doing in and out of the computer screen. So for the magnetic field, I have to the external magnetic field to figure out if there is going to be a torque. I have to figure out how to put it in this drawing. Well, I could put it also in and out of the screen. So let's pick one. I could say, here is my magnetic, that's my mu. My mu points out and it has a value of IA. A is the area of this, so L times L, the area of this loop. Okay, for the magnetic field, now I have to decide how I put it in this drawing. Okay, so if I put it like this, say for instance, and then I say B, this is my magnetic field, B. And then I put it everywhere, not just at that location, but here is everywhere, like that, everywhere around the loop, everywhere. There is a magnetic field that is that much. If I cut off the magnetic field, I'll tell you, only this region has magnetic field. So in this situation, everything has magnetic field, is into the plane of the screen. Will there be a torque? Yes or no? What do you think? Now I use this formula. Now I specify the B field. I have to give it a value, 5 teslas. Teslas is the value, is how the units for the magnetic field. Based on the choice and the direction of the choice I picked, which is into the computer screen, what is the torque in that case? Anybody want to answer that on chat? What does the cross product mean? It means the angle, the sign of the angle in between. The mu and the B, what is the angle, right? Okay, so makes it, believe it or not, it makes it go a little faster to do it this way. We can do the forces in a second. We're gonna do the forces in a second, just to make sure we understand what we're saying. But right here, this says that the torque is 0, right? Because in this case, for the one I picked, the mu, the magnetic moment, and the B are anti-aligned. One points out, one goes in, but the angle in between is 360. Well, sorry, no, it's not 360, it's 180. So that means anti-aligned. And that's 0. When you take the sign of that, that's 0. Okay, so when they're aligned or anti-aligned, the angle gives you a sign of 0, so there is no torque. So this would be the situation of no torque. That would be my drawing, where if I drew this immediately just by thinking of this formula, you should be able to say, oh, that's 0 torque, no torque. Okay, so we'll think about it in terms of forces in a second. but just in terms of this equation since they give it to you. So that means that I wouldn't be twisting my loop. My loop is not going to twist. Why is this important? Of course, this is important because this is very useful for electric motors. Most of them, all it is a magnet, and then you have a loop, and the loop carries a current. And the current is being delivered by what? By the battery. So you have a battery, you have a current in the loop, and then you have an external magnetic field. And you want to know if you're twisting your loop. If you're twisting it, you can turn the whole thing into an engine. If you're not twisting it, then it's not doing anything, it's sitting there. But if you're twisting it, you can make it turn. And now all of a sudden you can, well, we're not doing the electric motor just yet. We'll come back to it in more detail, but yeah, that's sure, of course. Okay, so that's kind of like, you can use that for a motor for sure. Okay, anyway, in this situation, there is no torque, zero torque, great. So how would I draw a case in which there would be torque? Okay, so now I'm gonna draw a case with torque. So I have to carefully erase the B fields. That's the only thing I want to erase. Let's see if I can do that. Nope, I cannot, without deleting anything else. Okay, anyway, I close that up again. So I'm gonna draw a B field that would result in a torque. The one I drew didn't result in a torque. So the loop would just stand there, would not rotate. There is no torque. How would I do a B field that does have a torque? Well, if I drew a B field like that, in a drawing like this, again, I want to keep my drawings like this, okay? That's what I want to do. I don't want to draw, but if I draw a thing like this and I draw B field like this, to the right or to the left, what do I mean by that? What I mean by this drawing is, I mean that now there is a 90-degree angle between the B field. The mu is coming out of the board. The magnetic moment is coming out of the computer screen, but the magnetic field is going to the right. So there is a 90-degree angle between the two. Then when I take the cross product, now, now in order to figure out what direction is the torque, we can do that with it. We need the cross product now. So now I'm gonna do out of the board, and then I'm gonna do the B field to the right. So it's like this to the right. So it's out of the board, sorry, like this. Okay, so the whole thing will twist in one particular direction. Let's go back. Actually, I can show you how to do that in a more reasonable. Let's go back. Let's do it with forces just to see how this works, and then we'll match up to this equation. But let's do forces very quickly as well as this equation. Again, as I mentioned, you don't need to do that equation, but we're gonna do it anyway. So what we're gonna do is we remind ourselves of the equation, but then we're gonna write forces. Now the forces we already did, let's see if we remember how to do that. And we pick the right directions for everything. So we're gonna have the case, the original case, we're gonna have the current that we chose. Again, sorry for being a little slow. I do need to get to the other PowerPoint, but I think this is important to clear up and to be very clear about how the forces and the torques relate to each other. Okay, and then you'll figure out everything. It's pretty easy and you won't waste a lot of time. So the mu is IA. So the I, we said, goes this way. And we said the mu goes that way. So we decided that from the right-hand rule, pointed up, right? Now, we want to figure out, is this going to turn? Is this going to twist one way or the other? Okay, it turns out it will, but I actually figuring out from the torque, from this formula, this should have a vector. That's not that easy because it's not clear what you mean when you say the torque is up. The torque turns out to be up because you go like this, you go like that, and the torque is up. But that doesn't help you so much in figuring out the direction of the rotation, which is what's important here. So, so you can use this formula more than anything for the magnitude. Let's try to figure out the sense of the rotation. How would the loop rotate, this way or that way, if there is a torque? Well, we already decided which case has a torque. But let's start again from the step one. When the B field is like this, there is no torque. Okay, let's go one step at a time. I definitely want to make this clear. I don't think it should be clear right now so far, but I think we're going to make it clear. Okay, so mu and B. So the B is into the board. So in that case, we said this is 0. So we have to find out that the torque is 0 for that case. Let's do this with forces and one step at a time, okay? So forget the mu, just for 1 second, forget the mu, the magnetic moment. Let's just think about the force on this segment of the wire, then the force on that segment, then the force on that segment, and then the force on that segment. Okay, and then once we figure out, is there a force, in what direction, then we will see in our mind very easily whether the forces are twisting the loop or whether they're stretching the loop. What the hell are they doing to the loop? If they're stretching the loop, then that's not a torque. That's just like the loop is fighting the force. Okay, so let's figure that out. So we have a B field into the board. We have a current that goes up in this section. So we're gonna do first that one, number one, that's the number one. So we're doing number one. Okay, so what formula do we need? We need the force formula. We already wrote it down. It goes like L. We turn the current into a vector, B, I, and then we cross it with the B field. Okay, so based on that, what direction? So now we do our right-hand rule. This one we're familiar with. We did it already. We should be fine with it. Okay, so we take our fingers, we put it in the direction. I'm using this equation now. I take my fingers, the right-hand rule says, put it in the direction of the current. Now I curl my fingers into the direction of the B field. That's this way. And then my thumb points into the direction of the force. Okay, so if I did this, do that, the force is to the left. If you disagree with anything I do, please let me know. Okay, I do want to make this clear before I move on. You do need this. So I'm sure there's going to be some example just like this, either multiple choice or multiple choice question. I can put that easily in multiple choice questions actually. So there will be stuff like this. So I would be saying, oh, I draw a figure for you. And I say, okay, is there a torque? Yes or no? I could also ask, is there a flux? Yes or no, in this situation? So I'm sure I'll do that actually. Okay, so I say I, B field into the screen. My thumb points to my left. So I'm drawing a force in that direction. That's F1. Okay, if you disagree, let me know. That's what I'm getting. Up, into the screen, to the left. Now I'm gonna do now at the top, here, this segment, I go segment by segment. I say, is there a force in each of them? Okay, so in that case, I have to put my fingers like this. Then I curl into the computer screen for me, so my thumb is pointed down. So the force at the top, I'm always using my right hand. So the force at the top would be down like that. So F1, that would be F2, say. Sorry, oof, very bad handwriting there. Okay, let me erase it. That's not gonna help. Okay, the force is down. Let's just leave it there. I don't need to put a force, 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 force. Okay. At the top would be down. Now, how about it on the left side? Well, then I'm gonna have to go, the current is going down in that case. Then I curl my fingers into the computer screen again. I'm doing a weird position, but that's how it works. So down, computer screen, my thumb points in the direction of the force. I'm coming up with this direction of the force. And again, please agree with the directions I have, otherwise it's not gonna make sense. Okay, if I did it, the current here is going to the right, so the force would be that way. So the net force in this situation, all these pieces are pulling in. What you're trying to do is you're trying to squeeze the loop, but you're not twisting it. You're not creating a rotation. So there is no torque, right? Torque is what makes the loop turn like this angle, either into the board this side or the other side, right? So this doesn't have a torque. This is just a situation where you're squeezing the loop on all sides. Okay, now let's do the second case, the one that does have a torque, and then we'll figure out which side is coming out of the board, which side is going into the board, and then that's it, you know, everything. So the case that does have a torque is this case. I'm gonna do the same drawing as before, and again, I'm gonna keep drawings like this, okay? Please get used to this kind of drawing. Those are the ones you will see in the exam. You're not gonna see other kinds of three-dimensional drawings in there. I always keep it in this kind of format, in and out of the screen. So the I goes like that. Now we're still going to have the mu coming out. That's the other right-hand rule. You wrap your fingers around the current, the mu comes out of the computer. Then we say the torque equals mu cross B. So we said, okay, if we have a B field going that way, everywhere, so like that, so there's a B field everywhere to the right, then this tells you that, yeah, there should be a torque. Now let's do it with forces, see if we agree with that. So again, this is a B field to the right. So how would I do the force then? So I get the I, can you see hopefully my hand is not disappearing. I guess if I keep it close enough, it won't disappear. So I do the I going up, now B field to the right, and now my thumb would point into the computer screen in that situation. So that would be a situation where I would have to draw, if I draw a force, then I would have to do, in a drawing like this, I have to do the cross, that would be a cross like this here. That's the force. The I is going up, the B field is going to the right, my thumb is, I'm using the right hand rule, so my thumb points into the computer screen. So that's into the computer screen on that side. Okay, how about here at the top? Okay, so let's do all the pieces here. So now here, now let's think about this. Okay, this is kind of, okay, let's see who gets what's happening here. Let's see. Okay, I'm kind of gonna give it away by asking in this manner, but what is the force? Is it at the top? What is the force? Is it out of the board, into the board, or zero? Pick one. Okay, well, we have some disagreements. Okay, so even though I cannot give it away by the way of asking, okay, question mark, good. Again, look at this formula again. You gotta be comfortable here. You can see already that even if you've been doing very well, if you're not comfortable here, you could end up losing a lot of points. You don't want to do that. You have to just play around with these right-hand rules. Okay. So again, it does help a little bit, this one, to see if there's a torque or no torque. In this situation, that tells you there is a torque, but let's do it with forces. Okay. Again, you want to use, when you're doing the force, you use this equation. There's a cross product. We're doing cross products constantly here. So whenever there is a cross product, you always ask yourself, what is the sign of the angle between the current and the B field? Now here in this piece, on that side here, what is the angle between I and B? It's 90 degrees here, right? There's 90 degrees between I going up and B to the right. So sine of 90 is 1. So then the force, sine of 90 is 1. So then the force would just be L, the length of the wire on that side, times I, the current, and then sine of 91 times B. That's it. Well, what is the angle between the current and the B field at the top? What is the angle there? Here, the angle is 90. What is the angle here? Theta. What is the angle between I and the B field? The B field is to the right, I is to the left. What is the angle between the two? 180. Right, 180. So if you take the sine of 180, it's still 0. It's this sine of 0 is 0, sine of 180 is 0. Right? So those are anti-aligned. At the bottom, they're aligned. But the angle, sine of the angle is 0. Now they're aligned at the bottom. So sine of 0 is 0. So this is going to give you no force. So at the top, the force equals 0. At the bottom, the force equals 0. But on the sides, the force is not 0. Please make sure you agree with that, because on the sides, the angle is 90. Right? The current is going up. The B field is to the right. That's a 90-degree angle. That's not 0. Okay, so there is a force on the right side. There is a force on the left side, but there is no force on the top and bottom. The forces on the top and bottom are 0 in this situation. Okay, that's different from this drawing. That's not inconsistent. Here there is a force on the top and bottom, but there is no torque. Here there is a torque, but there is no force on the top and bottom. Okay, make sure that you agree with that, because that is going to show up. So think about that a little while, make sure that you're with it. because it will show up for sure in the multiple choice question of the exam. Anyway, so I just would like this kind of drawing. So there you go. So anyway, so now we figured out now for the direction on the left side, you tell me, is that we agreed there is going to be a force, of course, because the angle is, again, now one is to the right, there is an angle of 90 degrees in there. How about, what is the direction of the force? Is it out of the computer screen or into the computer screen? You pick one. Everybody agree? So what Isaias is saying is this: on this side, the force is out of the computer screen. On the right side, the force is into the computer screen. Okay? Why is that? Well, let's do it. Well, it's hard to do it, but you would go like this. Okay, no, you cannot see my hand. That's a tough one. Boy, you can't see my hand if I'm doing it. Let's see how it. Okay, I guess I could do it this way. I'll have to twist my hand with my other hand to show you. Okay, so you would have, you're picking, my fingers are going in the direction of the current on the left side of the loop. It's going down on the left side of the loop. The current is going down. So that's my fingers are going down. So far so good. Then I twist my fingers into the direction of the B field, which is this way. And then my thumb points out. So therefore, that's correct. So again, I'm sorry if you can't see very well. I'm having trouble with getting myself on camera and so on. I'm doing a reasonable position of my hands. But yeah, we should all agree that that's Isaias and Ajinkya are correct. That's out. So on the right side is into the board. That's easier, actually. Let me do that one again. That's much easier. I don't have to start going like this. So how I did that is current up. That's the direction of the current. The B field is to my right, and therefore my thumb points in the direction of the force. All I'm doing is I'm doing the right-hand rule for that equation. That's what I just did. The angle in between I and B is 90 degrees. Therefore, the magnitude of the vector is L times I times B, and it points into the board. So that's why I drew a cross for the force here. Okay, I, B, my thumb points into the computer screen like that. I think you see it. Okay? Okay. So the question then is, will there be a torque? Well, of course, what I'm doing is I'm punching this one into the computer screen and I'm bringing the other one out of the computer screen. So of course I'm rotating it. And if I want to know, that's the direction of rotation. I just did it. Into the computer screen with my right hand, out of the computer screen with my left hand. That's the direction of rotation. If I want to know the magnitude of that torque, well, I can use that formula again. So let's use it. That would be mu, which is IA. Since it's one loop, just keep it IA times B. That's it, you're done. Okay, so there, in this situation, there is a torque. The torque is IAB. Okay? That's it. I is the L times L, is the surface area of your loop. Okay, that's it. There's nothing else. Let's move on. Any questions about that? Again, we can come back to it during the review time. Definitely, I can ask questions in this setup. I could also ask, does the B field have a flux, for instance? Here it has a flux on case 1. On case 2 here, there is no flux through the loop. So the B field is not piercing the loop. So there will be no flux. As in Gauss's law, when you calculate the flux, you got to pierce the loop. So if I'm talking about fluxes, here there is a flux. This is a situation of flux. The B field is going through the surface area. And this would be a situation of no flux, zero flux. That's a different issue, okay? I'm just telling you, I could ask several things about setups of this kind. Could ask about fluxes. Fluxes are BA, or I could ask about torques. Also, I could ask about forces. So there are several things. There's room to ask different kinds of questions in the same setup. We'll come back to it in preparation for the exam. But yeah, definitely, my intention, I can already tell you my intention is have a bunch of multiple choice questions, like maybe even 3 or 4. all with this kind of a loop, and then ask different things about it. Which one has a torque? What is the value of the torque? Which one doesn't have a torque? Which one has a flux? Okay, so anyway, we'll come back to it, but yeah, I will put that in there in the multiple choice part. Next, PowerPoint. Okay, I'm gonna run out of time on this PowerPoint. That's fine, but let me get it started at least to get you thinking about how the two PowerPoints, how they fit together. Now, where's my 28, PowerPoint 28? Okay, wait a second. Oh, there. Okay, so the logic, even though the PowerPoint all of a sudden included something that was illogical in there, but the logic is pretty good. The thing though is that these two PowerPoints really do belong together. Because let me give you an example to show you that the two PowerPoints do belong together. So what have we done so far? Let me give you an example also. In fact, this example will again show up in the exam for sure. This will be one of the long format problems. Now, suppose I have, so far we've done is this. We did part one. We wrote an equation for the force on a wire if there is an external field present. Okay, so we have a wire. That's what we were just doing. It carries a current up or down. And then there is a B field in the entire area here. I didn't explain how we got that B field in there. And then I say, okay, so therefore for this part, the force is, we just wrote it down, L I cross B. That's the first part. That was the previous PowerPoint. But now we're in PowerPoint number 2, but we can fit it into one single problem. Now in this PowerPoint, part 2, what you ask in part 2 is, well, how the hell do you generate that B field which I drew in part 1? How do I do that? How do I put a B field in there? Well, you know, for part 1, you can just say, okay, I put a magnet. So that would be one way to do it. But then you would still want to know, well, why does a magnet have magnetic fields? It turns out magnets have magnetic fields because the electron magnetic poles, dipoles, or magnetic moments, they're aligned. The electrons are in a configuration where they're all aligned and they're all helping each other out. But when you think about it for a little while, then you say, well, why is this atom, why does it have a magnetic moment? Well, the fact is that at that point, you're actually talking about quantum mechanics, but you can think of it in a non-quantum mechanics way. So this would be another situation where it's not really useful to talk about that too much because you would definitely get into quantum mechanics yet again. Nevertheless, you can forget the quantum mechanics for 1 second, and you can think of electrons in the atoms in a classical sense, even though you're not going to get red values for anything, but you can still think of it like, oh, well, what is an atom? Well, an atom is a proton, and then there's an electron that we can think of it as orbiting. Of course, that's not what quantum mechanics says, but close enough. So let's think about it in a simple way. And so if you have an atom, and you have a proton, and the electron is going around and around and around, well, what does it mean to go around and around and around? Well, that means it's a current. If you have an electron moving around, then the electron has a charge, so you can think of that as a current. So it turns out that currents generate magnetic fields. So that's the second part. That's what this is going to talk about. It's going to say, if you have a wire or even a moving charge by itself, the fact that it's moving creates a current. And that by itself produces a magnetic field. So we're going to need equations to tell us what is the magnetic field of A, a moving charge, B, a current. Okay, notice that there is a symmetry there that is very clear. There's nothing really mysterious going on. In part 1, we said this. We have a magnetic field, and then we said first we had moving charges, and then we had a moving charge in a circle. And then you say, well, a moving charge is the same thing as a current. So then the next step is, okay, we have a wire with a current. Great. So part 2 has the same situation happening. Now you're going to have a moving charge, and that's going to generate a magnetic field. And then you're going to say, well, but a moving charge is just like a current. So then fine, then you're going to have a wire, and that's going to generate a magnetic field. What we can do then is we can use that here, because on part one, we had the external magnetic field. On part two, what's going to generate that external magnetic field, guess what it is? It's a wire carrying a current. That will generate a magnetic field. So what ends up happening is this then, and we're going to calculate exactly how much, how strong. But what ends up happening is this. You put a wire with a current. This wire generates a magnetic field at the location of the second wire. Now, the second wire is itself carrying a current because it's in the external magnetic field of wire number one. Then wire number two suffers a force. So it turns out that wires side by side interact with each other. They affect each other. There is a force between them. Okay, so that will definitely, we're going to have that example in the exam for sure. Just basically what I just said, two wires, one wire generates the magnetic field, the other one suffers a force. Or you can flip it. It doesn't matter which is which. Of course, it doesn't. You can think of the first wire or the second wire as being the generator of the magnetic field. The other wire is in a magnetic field, so there is a force on it. Okay, so we'll get there. Well, hopefully by the end of today, I can cover the end of that problem. I have 30 minutes. The second problem that I want to cover is the one I started out with. If you just understand those two problems pretty well, then there's, pretty much every problem is kind of like that. So the other problem I talked about is you have two protons and they're moving. And so because they're moving charges, they generate magnetic fields, not just electric fields. And then since there is a particle in a magnetic field of the other particle, then there are forces involved as well. So it doesn't matter whether you have wires carrying current or moving charges. It's the same thing. Okay. Let's see how that would work. So in order to make that work, we have to now start talking about the magnetic fields produced by wires or moving charges. Here they start with a moving charge, but again, a current is a moving charge. So it's just the idea is the same. You just rewrite the equation a little bit. Now, nevertheless, let's spend a little bit of time on this equation because I know this equation bothers people because it's a little unclear what you mean by it. When you first see it, it seems a little complicated. As soon as the little hats start showing up, people start to get a little tense about it because they don't exactly know what to do with the hat thing. But let's try to demystify it so it's pretty clear what you're doing and it's not that problematic. So this is the equation that you can use. Now in practice, we will do something simpler than this. There's an Ampere's law that we can use to figure out what the magnetic field is going to be. Nevertheless, you could use just this equation. So let's talk about the equation, make sure we know what to do with it. So basically, here is a moving charge. Now the charge, now for once they do the drawing like I like to do them, like I keep them in the exam. So they're saying the cross, see they're telling you the cross here is the charge moving into the plane. So you have a charge and it's moving into the screen, computer screen. It really, since it's a positive charge, I guess, did they say it's a positive charge? Let me, 1 second, I'll tell you if it's a positive charge. Yes, it's a positive charge. So it's a positive charge moving into the computer screen. Since it's a positive charge moving in the computer screen, you can also think of this as a wire carrying a current into the computer screen. It will be the same thing. Okay, but now they're starting with charges. Okay, so therefore you have a charge moving in. And what we'd like to know is figure out the B field due to that charge. Okay, so in order to figure out the B field, you got to figure out the B field at a particular point in space. So you pick a point in space and you want to know what is the magnitude of the B field at that point, and also what is the direction of the B field at that point. So let's pick a point. It doesn't matter which, but it's easier to pick the ones that are like in the x-axis or in the y-axis. So let's pick, say, the top point here, right there. That's our point in space. Okay? Okay. So let me read. So the point of space is right there, right on top of the charge, right where the arrow is, right there. That's our point in space. So what we want to know at that point in space, what is the magnitude of the B field, and also what is the direction? Now they're already giving you the direction. All we're going to do is figure out that the formula agrees with the drawing. Okay. So in order to figure that out, we got to figure out, okay, what is the velocity? Well, the velocity is into the board. So when I do my right-hand rule, this is a cross product. Cross products are always right-hand rules. So I have to do the direction of the B field, the direction of the velocity is into the computer screen, right? Now, what you would like to know is what is the direction of this R hat? Okay, so the R hat is very simple. It's a unit vector. The magnitude of it is just 1. So when you write the magnitude of the formula, the R hat doesn't show up. But for the direction you need it, where is this R hat? It points from the direction of from the position of the charge. You see unit vector from the point charge towards the location in space that you're measuring the thing. So we picked a place, the charge is here, is the cross, that's the charge. Now we picked a point in space, which is at the top. So our R hat, in this case, points straight up. That's R hat, is straight up. Has unit magnitude, points straight up. Okay, so now we're gonna use the right-hand rule for the cross product. B, the velocity is into this computer screen, right? The R hat is up, so my thumb points to the right. So what does that right-hand rule tell me? It tells me that the B field at the location I chose must point to the right, like that. And the magnitude of it is B, that's the direction, to the right. Well, that agrees with the drawing. I just found out whatever the drawing is telling me. At that location, the B field points to the right. And the magnitude of the B field is mu0 over 4 pi. And then you forget the R hat because that's a unit vector, but you say QV, that's the velocity of the charge, divided by R squared. That's the magnitude of the vector. The magnitude, the R hat doesn't show up in the magnitude equation. Of course, it's just unity, 1. So that's, I can put 1 there, and now I've included it. Okay? Okay, so let's do one more case here. If we did this one, R hat would point in this direction. So then I would have to do this, the velocity, then I curl my fingers into the R hat, and then my thumb points down in this situation. So therefore, I have to draw a B field down because my thumb points down right there. Well, that's what the drawing is saying. So the B field is just going around in a clockwise sense in this drawing. So each point has a B field, but the direction of the B field keeps changing around the wire. Well, this is not a wire, this is just a single charge, but it will be the same thing with a wire. There is a wire drawing a little bit, but it will be the same thing. And what will happen when we do a wire, we will write an equation for the B field of the wire. And then we will have yet another right-hand rule to make the sense of the B field, clockwise or counterclockwise, come out fast. So you'll be able to say, oh, it's a negative or a positive, meaning clockwise or counterclockwise. So this case would be, if you think of it like a wire, where you'll see it agrees with the wire thing, okay? So what we're doing right now is kind of like the same thing as the wire. So if instead of a charge, I have a wire and my wire is going into the board, I'll already tell you the right-hand rule that's gonna give you all the right information. So what they like to do is they like to come up with yet another right-hand rule. Now in this right-hand rule, what I'm gonna do is, this is different, okay? I'm sorry to confuse you. Maybe once you get used to it, it's actually not confusing, it helps. But at first, you can't. When I was doing the right-hand rule I was just doing, that's the right-hand rule that applies to whenever you have a cross product. Since there's a cross product there, that's why I was using the right-hand rule. But now they come up with a different one just to make things go faster. They say, if you put your thumb in the direction of the current, so the flow of positive charges is the direction of the current, so this would be into the computer screen. I put my finger into the direction, my thumb in the direction of the computer screen, then my fingers wrap around in the direction of the magnetic field. So in this case, it would be clockwise. So I put my thumb in the direction of the current, and then my fingers wrap around in that way. Now there is another drawing. Okay, let me go to the other drawing. So that would be, let me go to the wire. Okay, it's the same thing. I'll come back. But let me, am I going to run out of time? No, I'm doing okay. I'll come back to this. Let's look at this drawing, because that's the right-hand rule I was talking about right now. Look at this drawing. You see, you can tell by the hand in here, they just now giving you an additional right-hand rule. So let's see. So let me write this down. Maybe you should put it on your notes in case you got confused about what happened. So we have a right, let me write it down. Yeah. We have right-hand rule for cross product. Then we have a right-hand rule for direction of the magnetic moment. Now that one, you're not gonna use that much unless you wanna figure out torques and so on, but you're not gonna, yeah, you could use it for torques if you want to. Direction of, you don't need it really, you could do it just with forces, but you can use the torque formula from the magnetic moment. So the right-hand rule will be for the direction of the magnetic moment. Okay, and then there would be this right-hand rule right here. That's the third one. Right-hand rule for direction of B field due to a current carrying wire. Okay, so those are the three. Now the first one is the one you use all the time. That's the one you use all the time. This one we're covering right now, that could be useful when we have two wires. That could be useful so that I don't have to waste a lot of time figuring out from above what the R hat and all of that. You don't want to start thinking about R hats. It's a little easier to use this right-hand rule instead. Okay, so notice what the right-hand rule they're telling you here. The right-hand rule just gives you a sense of direction. It doesn't, again, it's not really telling you the exact, it just tells you, is it clockwise or counterclockwise? It's to solve the sign ambiguity, that's it. That's the only reason. So what they're telling you here is you put your fingers around the wire, sorry, your thumb in the direction of the wire, and then your fingers curl in the direction of the B field around the wire. So notice what they're telling you. They're telling you the B field keeps changing direction, just like the one above, right? So depending where you are, the B field points in a different direction. So if you're right there, the B field points straight down. If you're here, it would be point to the left if you're looking from that angle, and right if you're looking from the other angle. But anyway, you can tell from the drawing that the B field keeps changing. Here is up, here is down, here is to the right, here is to the left, right? So it's curling around the wire, and the thumb tells you how to think of that. The thumb points in the direction of the current, and the fingers curl around the direction of the B field, point in the same direction as the B field. Okay, I'm not really sure. I'm not totally 100% sold on this right-hand rule. I'm teaching it because it's in here. What can happen is that these right-hand rules we're doing now kind of seem to get you confused with the first one. The first one is the most important one. That's the one you're using all the time because the cross products are showing up everywhere. But yeah, maybe you want to keep this one in mind as well. This one perhaps is the least useful one, but this one you can probably keep it in mind to speed things up. Okay. Great, so what do we talk about next? Well, we could start trying to solve the problem, but let's talk about something. Let me tell you something very useful that will happen. There is such a thing as an analog of the, you know how we got electric fields from Gauss's laws? So there is something like that is called Ampere's laws. So let me tell you where to use it and where not to use it. So what we would like to do is, instead of using this formula, this is kind of unwieldy, you know, it's not like that easy. Now what they're saying, okay, if you wanted to use this formula and you wanted to figure out, you see why is this not sorry, yes. This is just for one charge, right? So we got this formula here. Now, That's a charge. So that's the formula we got. Now, suppose you want to not talk about wires because it's easier in the lab to study wires than to study actual moving charges. You don't see moving charges, but you do see wires. So let's use a wire. Well, they're trying to tell you, well, if you want to do a wire instead of a moving charge, now you end up with a differential equation. So that's why they have a dB here and they have a dL, where D is a piece of the wire that you're talking about. That's the L is the length. D, you're taking derivatives, you're taking chunks of the wire and integrating. So then they do a case like that for you here, where they're integrating this wire. They want to know, you pick a point in space, that's your point. And you want to know what is the B field do to the wire is carrying a current at that location. Now we already know the direction because we have the right-hand rule. You put your thumb in the direction of the current, your fingers curl into the B field. So that what they're trying to tell you here is the direction is clear enough. They have a cross there. So that the B field is into the board, into the computer screen. Okay, but it's not just you want to calculate the magnitude of it. So now they're trying to tell you, well, really, if you want to do that, you must do an integral. Okay, so they're checking little pieces of this wire and so on, and then they integrate it along the wire, and the angle keeps changing because the point is at a different location for a different piece. So if they go to a different piece, when you do the integral, the angles change and so on. Okay, that's a little messy. We have enough trouble as it is. Of course, we should be able to do the calculus, but let's just avoid the calculus. How did we do that before? We use Gauss's law. So let's avoid the calculus with something in magnetic fields. So there is such a thing. So we're gonna get this equation, okay? So initially in this PowerPoint, they got this equation by integrating. We're gonna get it a different way. That's the goal, get that equation without doing any integrals. Nothing, you don't have to integrate over the length of the wire or something like that. But we're gonna get the same equation. Okay, to do that, we have to talk about this Ampere's law. Where is it? Right here. Oh, no, that's, where is Ampere's law? Again, they do an integral here. I don't wanna do integrals. I wanna use Ampere's law. There you go. So we're gonna, this is the last thing I'm gonna explain today. I'm gonna stop here. Okay, I don't wanna overload too much today, but the equation we wanted to find out is that equation, the equation for the B field of a wire. Now we know the direction is already being given to you right here. You put the thumb in the direction of the current, and then you curl your fingers in the direction of the B field. The direction of the B field keeps changing in space. It's going around and around and around your wire. But we need to know not just the direction, that's great, but we need to know what is the value of the B field at a particular point. Where is the value of the B field? Right there. Okay, so here's the Gauss's law. It's a little different than, this is the Gauss's law analog. It's not really a Gauss's law, really. But this is what people use for B fields. For E fields, they use Gauss's law. For B fields, they use this right here. Okay, this is what happens. Well, they're giving the general statement right here. Here's the general statement. So I'm gonna spend a little bit of time here slowing down here just to tell you the result is pretty easy. It's the B field of a wire. We're certainly gonna use that. So what our goal is to have wire 1, wire 2. So we want to know the B field of wire 1, and then we can calculate the force on wire 2, or vice versa. We can flip them. We B field of wire 2 on wire 1, and so on. So we need this to tell us what is the value of the B field. So what it ends up happening is when you have a lot of symmetry, like same thing as with Gauss's law, there was a lot of symmetry. So we could use Gauss's law. So when the B field has a lot of symmetry, then instead of using Gauss's law, you can use Ampere's law, which is this one. So notice for Gauss's law, let me remind you of Gauss's law again, just so that we can compare and show that it's not the same. You're not doing exactly the same thing, but it looks very similar. Okay, so that you also have to worry about what the hell does that mean? The little circle thing. What does that mean? Okay, so let me write Gauss's law. Gauss's law went like this. What we did is we did the flux, and we said Gauss's law was for electric fields, and then we said we integrate over surface. We pick a surface and we integrate over the surface, and then we do E dot dA. So we take a little chunk of the sphere, so we're calculating a flux. E times A was a flux. And then that was equal to the Q enclosed by my surface area. And then I divided that by epsilon naught. Wow, this looks very similar, right? There is an enclosed thing. There is a mu0 instead of E0. For the magnetic constant is mu0. For the electric constant, that was E0. I call that the permeability. Okay, anyway, so there is another constant. Doesn't matter what the name is. There's another constant in there. Instead of the Q enclosed, now you have a current enclosed. And where you had an area here, though, notice that's very important. That's quite different, actually, in the end. It's not really, you're not here instead of an area, you have a length of a wire segment of a loop. So DL has units of length. Here, DA has units of area. So it's not really the same thing, okay? Okay, so, but anyway, let's use it. So the thing that to use, so we're gonna use this. So the best example to use that with, now let me erase Gauss's law. So the easiest, most useful thing to use this with is just the wire case that we need in any case. So it's the easy way to calculate the equation for the wire. You can pick other cases. You can also do other cases. So for instance, the book will have a solenoid, the B field inside a solenoid. So when we did E fields, we did plates, we did capacitors. That was like the standard case for the where the Gauss's law was very useful for capacitors. When it comes to B fields, the useful thing is a solenoid, which just is a wire wrapped around with a current. So in the solenoid, the B field outside the solenoid is 0. And the B field inside the solenoid, the wire wrapped around a cylinder, the B field inside is constant. For a capacitor, it was the same thing with the electric field. If you had two plates, the E field outside the plates was 0. The E field inside the plates was constant. So for B fields, then solenoid is like a standard thing to talk about. We will do that. So that would be like the capacitor. This is kind of like, well, I'm just being helpful, trying to be helpful. Hopefully it helps. This is kind of like the capacitor of B fields. Let me, I'm just trying to be helpful. Okay, don't take it like this is a law of nature or something like that. I'm just reminding you what this solenoid is about. Okay, so great. So having said all of that, let's use this for one useful case, and that one that's the one you will end up using. There's also the solenoid that we'll talk about. The solenoid is in this PowerPoint at the bottom. I won't be able to get to it today, but there it is. Okay, so how do we use this? So now what you do with this thing is we're gonna take a wire. I'm gonna draw a drawing of the wire. And we're gonna decide that it's obvious, we're not gonna say why, because it's obvious from the symmetry that the B field, the magnitude of the B field can only depend on the distance from the wire. Okay, so it's symmetric. It can be, I guess, one value here and a different value over there. It can point in different directions, but the magnitude has to be the same. Okay, so it only depends on, so now what we're gonna do is we're gonna pick a loop. So now I'm gonna twist the wire is gonna come out of the board. So I'm putting the wire, so the current is this one coming out of the computer screen. And what I wanna do is figure out what is the value of the B field, say, at that location? So there's some distance r from the wire. So now the wire is in and out of the computer screen, okay? So I change the perspective. This drawing to that is a different perspective. Here the wire is like that, and the B field will turn out, well, let's look at this one. So then so it's coming out of the computer screen. So now I want to know the B field at that location. What is the magnitude of it? So it turns out that to do that, all I have to do is pick a loop around the wire like this. Kind of like we chose a surface in Gauss's law. Now we don't choose surfaces. Now instead of choosing surfaces, we're going to choose loops, because this is an integral over a loop, not an integral over an area. So since it's an integral over a loop, when you're using Ampere's law, you don't choose areas, you choose a loop. Okay, so here's my loop. By symmetry, I know it has to be a circle. So now this loop is going to allow me to perform this integral, B dl. I want to know what is that integral on this loop. Okay, well, since I'm always at the same distance from the wire, the B field is not going to change. The magnitude of the B field will be the same here as here. As here, I'm always the same distance from the wire. So I'm not going to have one B field here and a different B field somewhere else. Since I'm at the same distance, that doesn't make any sense. Just symmetrically, from symmetry, you're saying it doesn't make any sense. So therefore, for this particular case, I selected a loop where I can just remove the B field from the integral. So then I'm going to have B times the integral of a path of a little piece of this loop. So if I integrate a circle around one loop, I get a circumference. So what does that equal to? What is the circumference of a circle? How long the circumference is, how much distance along the loop? How much is that? Okay, so it sounds like I'm complicating things, but this question is actually pretty simple. What is the circumference of a circle? How long is it along? 2 pi r, right? I'm just wanting you to say it. In the end, all you're saying is when you're doing this integral, you're taking little chunks of this circle, and then you're integrating them over one loop. That's what this is telling you to do. So that's just B times 2 pi r. That's it. 2 pi r, because that's the integral that you actually did. It's very easy, it's 2 pi r. That's the circumference of the circle. So that has to be equal to mu 0 times the charge, so times the current enclosed. What is the current enclosed in this case? Is whatever current is punching through your circle, that's the enclosed current. So that's just the current in the wire. So the B field therefore equals mu 0 I over 2 pi r. Wow, as we didn't do anything, but that is the answer. That's it. So if we go up, so that is the B field due to that wire. So if we go up, see if that agrees with what we had before. Way at the top. Where was that? There it is. Mu 0 I over 2 pi r. Okay, so that's the same formula. There are other cases where this Ampere's law is useful. This is one. You can get that immediately. So basically, in the end, so let me remind you what we just did. We went around, I have 3 more minutes, and then I'll tell you what comes next. All we did is we picked a loop that here, I have a wire. Let me do this. This is the wire, my pen, and I picked a loop at equal distance from my pen. And my pen is carrying a current. And then all I did is I integrated the B field dot dl. The dot is 1 in this case because they're aligned. So I didn't even have to worry about the dot. Actually, I ignored it. I didn't say anything about it, but it was always 1. Then I integrated over one loop. And since the B field came out of the integral because it's a constant over that loop, then I'm just integrating path elements of the loop, and I just get the circumference when I do this, the integral. Therefore, I get this formula. That's it. Okay, great. Now we have a formula. And we have this, so we have the magnitude and we also have the direction. So now we're ready to do the problem which we agreed to do, which is this problem. Okay, so what we have 2 wires, And we want to know, is the force attractive or repulsive? So I'm not going to have time to do this. This is, you can actually, one thing that could help, let's do it this way, actually. Why don't you try to figure, you're going to encounter this in the exam. So why don't you, I'm going to do it for sure, but instead of me doing it, just me doing it, how about you try to figure out? So this would be the question I'm going to cover in the next class. And you do have enough information at this point to figure this out. When is, you have two wires and you have two cases. We're going to put them in parallel, like in this drawing. And we can have two cases. We can have the currents in both wires going in the same direction, or we can have the currents going in opposite directions. One wire up, the other wire down. Basically, those are the only two different cases. So one thing you could try to figure out on your own, and then we can discuss it and see if we all agree on the answer, is in which case will the wires attract each other? When the currents are pointing in the same direction, or when the currents are anti-aligned? In which case will the wires attract? In which case will the wires repel? Okay? Well, actually, they kind of gave you the answer here, actually. So that answers my question. But let's try to see if we can understand that, if we agree with that statement. But you can see the statement, the answer is already in the PowerPoint. If the wires have currents in opposite directions, then they repel. They push each other away from each other. If they have in the same directions, then they attract each other. Okay? So there's a force on both wires. And each wire also produces a magnetic field at the location of the other wire. So they attract in one case, they repel in the other. So they give you the answer here. So that's what I'm going to try to make sure. And this case will be in the exam. Okay, so there's not going to be any waste of time if you think about this. Okay, so that's it for today. I used up the whole time. Pretty intense class. I'll get back to practical problems in the next week, one of them being the one we have in front of us. Okay, so that's it. That's definitely it for today. See you in the next class.